Okay. So, what we are going to do now is look at the relation between primal and the dual problem. What was the primal problem? The primal problem was max over min over x, max over lambda greater than or 0, L of x comma lambda. This was the primal problem. The dual problem, this is primal. The dual is max over lambda greater than or equal to 0, min over x, L of x comma lambda. This is the dual problem, and we want to understand how these two things are related. Now, to understand this, let us look at the one more definition of a different function. Let us call this function j, right. So, this is a function again, this is a function of x, right. So, what is it going to, so how are we going to define this function? Well, we are simply going to say this function is going to be f of x if h of x is less than or equal to 0 and infinity otherwise. This is very closely related to the earlier function that we looked at, just that we are now saying that instead of saying f of x plus lambda h of x, which is the Lagrangian function, we are just directly trying to look at a function j of x, where j of x equals f of x if h of x is less than or equal to 0 or infinity otherwise. Of course, you can think of this as maximizing over lambda our Lagrangian for a given x comma lambda also, right. So, anyway, so this is, let us say we think of this as a separate function, and now if you look at for any lambda which is greater than or equal to 0, right. So, let us say I fix a lambda, I ask what is L of x comma lambda, the Lagrangian, that is going to be simply f of x plus lambda h of x. Now, if h of x is less than or equal to 0, right, then this whole value is going to be f of x minus something, right. So, because we have fixed lambda is greater than or equal to 0, our Lagrangian function for a given lambda is going to take a value which is f of x plus a positive or a non-negative value times a value which is non-positive, right. So, this is going to be less than or equal to f of x, which means that this is going to be if this is going to be less than or equal to f of x if h of x is less than or equal to 0, right. So, on the other hand, if h of x is greater than or equal to 0, well, this value is going to be f of x plus some positive or a non-negative value, which is still going to be less than or equal to infinity. Well, why am I putting it this way? The reason is, now you can think of this L of x comma lambda as some kind of a linear function which is lower bounding the function j of x, right. So, in other words, what I want to convey here is that our L of x comma lambda for so we have fixed lambda greater than or equal to 0, and L of x comma lambda is less than or equal to j of x for all x, no matter where x is, right. So, the only two interesting possibilities are whether x is such that h of x is less than or equal to 0, it satisfies the constraint, or it does not satisfy the constraint. If it satisfies the constraint, it is this the Lagrangian function is still less than or equal to f of x. If it does not satisfy the constraint, it is still less than or equal to infinity, which means it is less than or equal to j of x, right. So, this is always going to be less than or equal to j of x, which means we can say that if I look at the minimum over x, right. So, this is for all x, which means in particular it has to hold for the minimum value. The minimum over x L of x comma lambda has to be less than or equal to minimum over x j of x. This has to happen, right. Now Now let us think about what is the minimum over x j of x. Remember, j of x is defined such that if the constraint is satisfied, this is f of x, otherwise it is infinity, which means that my minimum is simply going to be f of x star, right. So, where x star is like the optimal solution of the original problem that I wanted to solve, right. Now, remember, this held for any lambda. I picked an arbitrary lambda and I said that my Lagrangian function is lower bounding the j of x function. So, now which means that I can, because it holds for any lambda, it also has to hold necessarily for the lambda that maximizes this function, right. So, which means that max over lambda greater than or equal to 0, min over x L of x comma lambda is also less than or equal to f of x star, right. But what does this tell us? This tells us something interesting, right. So, this f of x star, where x star, what was x star? X star is kind of the solution of the primal problem, right. So, remember, this is the solution of the primal problem, of the primal problem. What is the primal problem? Just to remind you, the primal problem is the original problem that we wanted to, so is equivalent to the original problem that we wanted to solve, which means that if I solve this problem and find an x star, and if I look at the function's value, that will be the smallest possible value within the constraint set. Now, the interesting part is that we have shown that the maximization over lambda greater than or equal to 0, minimization of x, which means that we have swapped these two guys, is still less than or equal to f of x star, right. So, this is the primal objective, right. So, and what is this, right. So, this is simply maximize over lambda greater than or equal to 0. By our definition, this is g of lambda, where we just defined g of lambda as minimization over x L of x comma lambda. Now, eventually what are we essentially saying, right. So, which means that if I had solved the dual problem, if I had solved the dual problem, which is here, and I had gotten lambda star, if I solve the primal problem, I had gotten x star. Now, what we are saying is that this is simply g of lambda star, and this is less than or equal to f of x star. In words, all we are saying is that the value at dual optimum is less than or equal to the value at the primal optimum. Right. This is very, very interesting, right. So, what did we do, right. So, just to recap, we started with a constraint optimization problem. We converted it into a problem which was of the form min max, and we said that these two are equivalent, and that we called the primal problem, and we swapped the min and the max, we call the dual problem. Now, if you solve the dual problem, you will get some lambda star, and if you look at the function's value at lambda star, well, that function's value is in fact less than or equal to the primal function's value, right. So, which is optimal value, which is f of x star. We know that is f of x star. So, what we are saying is that, well, the solution, so if you solve the dual problem and look at the function's value of the dual function's value, it may not be equal to the primal function's value, which means that it does not mean that you have solved the primal problem. We know the primal is equivalent to the constraint optimization problem we set out to solve. Now, if you solve the dual, all we are guaranteed is that g of lambda star, the dual's value, is less than or equal to the primal's value, right. So, this condition is what is called as a weak duality, right. So, which means that your dual problem, which is easy to solve, gives a quick, an easy lower bound for the primal optimal solution, right. So, which is useful in a lot of cases, it turns out, right. So, we will not discuss those cases in detail now, but all I am trying to say is that in general, without making any further assumptions about the nature of the functions f for the constraint h or anything of that sort, we are saying that we can take any problem, convert it into a concave maximization problem, where the constraints are lambda greater than or equal to 0, call that the dual problem, solve the dual problem. The objective value of the dual solution is less than or equal to the primal optimal solution, which is the relation between the dual and the primal. Now, the very interesting part, again there is a, without making a very rigorous statement, let me give you the most interesting statement which will be relevant to the machine learning part later. Now, if, right, so if the functions that we are trying to look at, right, so the objective function, so this is the objective function and this is the constraint. If these functions are convex, then something very interesting happens, right. So, you do not just have weak duality, you have what is called as strong duality. Strong duality holds. This is a very, very powerful theorem, right. So, we will not prove this theorem, and let me just say that this holds up to some regularity conditions, some regularity which is not the focus of this broad overview. The optimal points should satisfy some regularity conditions, but the main the assumption that leads to this is the convexity of f and h, right. So, let us focus on that. So, if our function that we are trying to optimize is a convex function and the constraint that we have is also a convex constraint, then what this is saying is that you can either solve the primal problem or solve the dual problem, right. So, the objective value that you will get by either solving the primal problem and the dual problem would exactly be the same. That is what strong duality says, right. So, in other words, you can either solve min over x max over lambda greater than 0 L of x comma lambda, or you can solve max over lambda greater than or equal to 0 min over x L of x comma lambda. And in a lot of cases this may be easier to solve, right. So, I am not saying it is always easier to solve, there may be cases, and in machine learning you will see why, we will later see when you are discussing some algorithms why this is an easier problem to solve. And I will talk a bit about the algorithms that where such a duality view helps a lot after we finish the discussion now about constraint optimization. Okay. So, all we are saying is that, which is very good. So, if f and h are convex, then strong duality holds, which means that we can either solve the primal problem or solve the dual problem. But in general, if you solve the dual problem, the solution's value at the dual optimal is going to be less than or equal to the solution's value at the primal optimal. In the special case of convexity, these two things happen to be similar, same. Yeah. So, this is the first main result, and we will now in the next few minutes see what are the implications of this result, right. So, what can we understand from this result? Remember, initially we set out to understand, well, if I have an unconstrained optimization problem, then if I find an x star where the gradient is 0, then I am done, right. So, if f is convex, for example, then I know this is a global minimum, otherwise I know this is like local optima. Now, here we want to understand something similar for the constraint optimization problem. That is where we started off with, and all we are saying so far is that, well, we are nowhere, at least at this point, we have not really understood what are the conditions that a point should satisfy such that it is necessary or sufficient to be a local optima or a global optima. We are not talking about that at all yet. All we are saying so far is that if I want to solve the original constraint optimization problem, you can either solve the primal version of it or the dual version of it. If f and h are convex, then doing these two things are the same, of course, up to some regularity conditions on the function, on the optimality of the function itself, right. So this is where we are. So what we want to do next is that we want to kind of convert this understanding into a set of conditions that the optimal solution will satisfy, right. So that is what we want to focus on next. For that, let's do the following. Let's assume, right. So okay, so let's assume f and h are convex, right. So which means that assume okay, f and h are convex, right. So which means strong duality holds. There are some regularity conditions, again I keep mentioning that, but let's forget that for the moment, right. So assume strong duality holds. Now we have the primal problem, we have the dual problem. The primal is a min over x, the dual is a max over lambda. Let's say x star comma lambda star are the primal and dual optimal solutions, right. So what do I mean by that? So just to be absolutely sure, because we will use this, I am saying x star is simply the arg min over x, max over lambda greater than or equal to 0, f of x plus lambda h of x, and lambda star is arg max over lambda greater than 0, min over x, f of x plus lambda h of x. Let us say these are the optimal solutions, right. So now what we are trying to understand is, if x star and lambda star are optimal solutions, any optimal solution for this problem, then what conditions should they satisfy, right. So what are the the necessary conditions for x star and lambda star, right. So to be optimal, remember we are assuming that strong duality holds. In other words, in this case we are assuming f and h are convex, strong duality holds, and so we want to understand what can we say about x star and lambda star. Of course, we know x star is the arg min of this, lambda star is the arg min of the dual problem, but can we say something about the properties that these pair should satisfy? Okay, for that let us look at the following, right. So now if we look at so because strong duality holds, right. So by strong duality, now my f of x star, right. So of course, if I evaluate the function's value at x star, that is going to be f of x star. So that is equal to like g of lambda star, right. So that is what strong duality kind of tells us. Now, well, what is g of lambda star? G of lambda star is min over x, f of x plus lambda star h of x, right. So this is, remember, this is the g of lambda function, which means that if I plug in lambda star into this, that just means that this lambda I am replacing it by lambda star, right. So now what does this tell us? This tells us two important things. By strong duality, I know f of x star is same as min over x, f of x plus lambda star h of x, which means that the function's value at x star is same as the function's value that I would get if I minimize this function. Well, what does that mean, right? So that means that what should x star be, right? So this is remember an unconstrained optimization problem. This means the following should then hold, right? So if I look at the gradient of this function at x star, that gradient should be 0, because this is an unconstrained optimization problem, and because f and h are convex, we are looking at the minimizer, so which means that the minimizer's gradient will be 0, right. So which means then what we are saying is that this implies the first important condition for our x star should satisfy is that the gradient of this function, which is like del of x star plus lambda star del of h star, h of x star equals 0, right. So this is, let us say, C1, condition number 1, right. So this is simply because of strong duality, right. So any x star lambda star pair that satisfies the optimality, so necessary has to satisfy these two, right, which is good. Now something else also is true, right. So we look at the same exact argument, but then some other conclusion will also be true, right. So we say f of x star equals g of x star. Now we just said g of x star is min over x f of x plus lambda star g of x. So which means that this is the minimum over f of x plus lambda star g of x over all possible x, right. So minimum over all possible x, which means that I can plug in any x here, any x dash here, and f of x dash plus lambda star g of x dash will be greater than or equal to this value, right. So now let us say substitute this x as x star itself, which means that this has to be less than or equal to, because this is minimum over all x, in particular for x star also. So this is less than or equal to f of x star plus lambda star g of x star. You see why that happens? Because any x, I can plug in any x, and then the minimum is going to be less than that, right. So this is minimum over all x. Now this is a surprising fact then, right. So what we are saying is that the left hand side by strong duality, right. So this is by strong duality is f of x star. The right hand side seems to be, this is upper bounded by f of x star plus lambda star, sorry, this should be h, sorry about that, this is h. Did I use g somewhere else as well? No. Okay. Lambda star h of x star. Now what can we, what does this essentially mean then, right? So we are saying f of x star is less than or equal to f of x star plus lambda star h of x star, but we also know that lambda star has to be greater than or equal to 0, h of x star has to be less than or equal to 0, right. So because at x star, h of x star satisfies the constraint, so h of x star will be less than or equal to 0 and lambda star will be greater than or equal to 0, which means that this whole thing is going to be less than or equal to 0, which means that this I can upper bound by f of x star, right. So this is f of x star plus something, and that something is less than or equal to 0, so the whole thing is upper bounded by f of x star. Now we started off with f of x star, and we are saying here is a sum of two terms, and we are upper bounding also by f of x star, which means that the only way this can happen is when all these three things are exactly the same, right. So otherwise this cannot happen, which in turn means that the only way this can happen is if the second term is 0, which is lambda star into h of x star equals 0. Now here is another condition, this is a very important condition. So this is C2, this we will come back to the name a bit later, but yeah, so this is condition 2, right. So, so we have kind of derived two conditions now on what my x star comma lambda star pair should satisfy if f and h are convex, right. So any optimal solution necessarily should satisfy these two conditions. Now let me put them all together for you. Now putting all together, what are we saying? right. So, we are saying the following, let us say f and h are convex. Now, this implies strong duality. Now, this implies, let us say x star comma lambda star must satisfy the following. Condition 1, which I am rewriting again. So, lambda f of x star plus lambda del f of x star plus lambda del h of x star, lambda star h of x star is 0, and this is often called as the stationary condition. This is condition 1. Condition 2 is, well, we saw h of x star into lambda star has to be 0, and this is a very important condition, and this is called as the complementary slackness condition. It is called complementary slackness because either lambda star is 0 or h of x star is 0 or both are 0, right. So, it cannot be the case in particular that if at optimal h of x star is less than 0, strictly less than 0, it is strictly within the constraint set, then lambda star cannot be strictly greater than 0, right. So, then lambda star strictly has to be 0, right. So, that is what this is essentially telling us, right. So, the product of these two has to be 0, and that is why it is called a complementary slackness condition. The third point, well, these are the other things are straightforward, which we already know. H of x star has to be less than or equal to 0. Well, that is like a feasibility check, right. So, your optimal problem point should necessarily also be feasible. So, this is what is called as a primal feasibility condition. The fourth condition is, of course, there is a dual feasibility. What is the dual feasibility? What should lambda star satisfy? It should be greater than or equal to 0, right. So, this is the dual feasibility. These are something that we already know because, well, these are simple, right. So, any feasible point should necessarily satisfy these. What is interesting is that now we are also saying that if you have an optimal point, then it necessarily has to satisfy the stationarity condition and also the complementary slackness condition. Now, of course, these are necessary conditions, right. So, if f and h are convex, then the optimal point should necessarily satisfy these things, right. So, of course, again let me say that the x star and lambda star there should be some regularity conditions. So, modulo which are, I did not want to get into the rigorous part of it, but that is not the most important part. The most important part are these 4 conditions are satisfied for any optimality x star and lambda star. Now, the question one might ask is that, well, this is a necessary condition, right. So, if f and h are convex, then the optimal solution should satisfy this. Now, the question is, if one manages to find such a point, right. So, let us say I give you a point x star comma lambda star and claim that it satisfies all these conditions, then can we say anything about this point, right. So, again, so this is a very interesting result, and this is slightly involved to prove, so we will not really do that in this course. So, in general, right. So, if x star comma lambda star satisfies the above conditions, right. So, again, and some regularity conditions which we will not talk about. Think of the regularity conditions as just avoiding some kind of corner cases. right. So, because if you have to be like make a rigorous statement, you should have look at the corner cases as well. But in general, the idea is that if x star lambda star satisfies the above conditions, then we can say that this x star is actually a local minimum. Right. So, basically what we are saying is that so all okay, so maybe I will say that we basically if so this is the sufficiency part, right. So, let me write it this way. So, this is a local minimum. So, remember we said that for the unconstrained case, if the gradient at x star is 0, then it is a local optima, right. So, this is something similar is what we are trying to say here. If x star comma lambda star, let me just call it local optima to be safe, optima. So, if x star and lambda star satisfies the above condition, then what we have is that is a local optima, right. So, this is like a certificate. So, if I can show a x star lambda star which has the certificate that it satisfies these condition, then it necessarily, I mean, then it is a local optima, right. So, this is sufficient to say that it is a local optima. Now, put it together with the previous argument that we did, where if f and g are convex, because strong duality holds, these exact same conditions are necessary for optimality. Now, we are saying that it is sufficient for, irrespective of it is convex or not, it is sufficient for being a local minima, and we know that for convex problems local minima, I mean essentially there are only global minimas. Now, then what we are essentially saying now is that for convex problems, these conditions kind of completely characterize the optimal solution. So, they are both necessary and sufficient, right. So, so that is the main reason why these conditions are useful, and these conditions are what are called as the KKT conditions, named after three people, Karush-Kuhn-Tucker. So, so these are names of people who came up with these conditions, and these conditions kind of completely characterize the solution for a convex problem, and in general it also gives you sufficiency condition for any general problem, any general constraint optimal problem. So, the KKT conditions are I mean can also be written when you do not have just one constraint, which is the case that we have looked at so far in this discussion. You can the same kind of ideas go through when you have multiple inequality constraints and multiple equality constraints. Just for the sake of completion, I am going to put them down, right. So, now what is the general problem that we will look at is minimize over f of x, not just one inequality constraints. We will look at, let us say, hi of x less than or equal to 0 for several i's, right. So, I equals 1 to m. There are m such inequality constraints, and let us say Lj of x is less than or equal to 0 for all j equals 1 to n. There are n equality constraints, sorry, this is equal to 0. These are equality constraints, right. So, you have in total m plus n constraints, m inequality and n equality constraints. So, this is the problem that we want to solve, and you can of course now form the Lagrangian of this. So, which is going to be, before it was just x comma lambda, now each of these constraints will have its own Lagrange multiplier, right. So, it is going to be, let us call them u and v. Now, remember this is a vector. Now, these are also vectors, right. So, u1, u2 till um, and this is going to be v1, v2 till vn. For each constraint you associate a Lagrange multiplier, and then you write this function as f of x plus sum over I equals 1 to m ui hi of x plus sum over j equals 1 to n Vj Lj of x, right. So, this is again you can now try to argue whatever we argued earlier for this new Lagrangian, it will go through exactly. And so, the KKT conditions for this problem would look like the following, right. So, let me note them down separately here. The first one would be the stationarity condition, which would simply be lambda of f of x star plus sum over I equals 1 to m. Now, remember instead of del of f of x star, the gradient, plus now instead of the lambda we have ui's and vj's, which will be in the dual variables, which will be ui star hi of x star plus sum over j equals 1 to n vj star h lj of x star equals 0. Sorry, that is a gradient, right. So, the gradient of the Lagrangian function at the primal optimal variable x star and the dual optimal variables u star and v star is 0, right. So, this is the 0 vector, right. So, this is a vector. It was a vector earlier as well, right. So, this is condition 1. Condition 2 is our complementary slackness condition. So, that is ui star into hi of x star equals 0 for all I, right. Of course, this is this has to be specified explicitly only for the inequality constraints hi's. For the equality constraints, obviously this is true because x star is feasible, and so Lj of x star is going to be 0. So, you do not have to separately write this. So, this is only relevant for the inequality constraints. So, this is the complementary slackness condition. Cs is complementary slackness. This is the stationarity condition, and we have the usual hi of x star is less than or equal to for all I, Lj of x star equal to 0 for all j. These have to be satisfied by any optimal solution. So, these are feasible. Feasibility, what feasibility? These are primal feasibility, and finally the dual feasibility, which just say ui star is greater than or equal to 0, right. So, for all I, these are dual feasibility. So, these are the general KKT conditions, and this holds for, as you can see, any general optimization problem which have inequality constraints and equality constraints put together, right. So, this is the most general form of stating the KKT conditions. Though we looked at the arguments with the single inequality constraints just for the purposes of exposition. So, you can do the same argument for the general case and it will go through. Okay, good. So, now we have kind of seen the equivalent of the first order necessary conditions and sufficiency conditions depending on the functions for constraint optimization problem, and KKT conditions are the right way to look at them.